So we're doing lesson number 4 of our energy unit, and we're going to start looking at heat and heat capacity. So I'm going to start by introducing a lot of new terms. Now these terms may be familiar because we use them a lot in English, just not necessarily correctly. Okay, so let's start with thermal energy. Now we've talked about kinetic energy. That's the energy of motion. And potential energy. Potential energy can be due to a lot of reasons. Right? You can have potential energy due to an object's position or due to its composition, right? Its state. So to explain thermal energy, let's look at a little example here. Let's say we have some water. Now in the water, you're going to have water molecules, a bunch of H2O, and they're going to be flying around in all different directions. Because they're moving, they have kinetic energy. Now they're also going to have intermolecular forces, which is going to cause some attraction between different particles. That is potential energy, right? And resulting in those forces between them. Now the combination of all kinetic energy and all potential energy is called thermal energy. In a substance of atoms or molecules caused by electric forces. Okay. Next, temperature. Temperature simply looks at the kinetic energy of the particles. Now, all the particles will have slightly different kinetic energies, so you can't look at every single one of them. So it sort of just looks at the average of all of them. And so the average kinetic energy of all the atoms or molecules, whatever substance you're looking at, is called the temperature. Next, heat. Heat should actually be a verb, but we use it in English like it's a noun, but it should be a verb. It's hard to get your head around when you're talking because we use it so often as a noun, but it means the transfer of thermal energy. And thermal energy always moves from hot to cold. It's called the second law of thermodynamics. In chemistry, you probably have heard it as entropy, which again is the second law of thermodynamics. So heat always transfers from hot to cold. Okay? And it's the transfer of thermal energy. Now there's 3 ways that you can do it. Conduction, if you were to touch something, right, you can transfer heat that way. Convection, so if you were to look at this little diagram here, if you're heating up the water, here you're going to have hot water. You're going to have colder water, so the hot water is going to move to the top, pushing the colder water down, and then the colder water gets heated. That creates these currents we call convection currents. And lastly, radiation. And so if you go outside on a nice sunny day, you can certainly feel there's a transfer of thermal energy there from the sun. It feels warm. So 3 ways to transfer thermal energies. So next, let's say we did want to heat up a substance. Maybe we want to take, let's just ignore our metal cube for a second. Let's say we just have a beaker of water and we want to heat it. Maybe we want to heat it from, 10 degrees to 90 degrees. Maybe we're making a cup of tea or something. Now, the amount of energy required to heat it depends on a few different things. One, obviously what I've already mentioned, the temperature change. If you want to go from 10 to 90, it's going to require a certain amount of energy. If you're only going from 10 to 20 degrees, less amount of energy. So how much you want to heat it by is going to depend how much energy is required. Also, how much water is there? Are you heating up just 1 cup of tea, or are you heating up a whole bin of tea to serve a whole bunch of guests, right? Is it 100 milliliters or 10 liters? Obviously, the more water you have, the more energy is going to required to actually change that temperature, the degrees that you want to change it by. And lastly, it depends what you're trying to heat. You're trying to heat water? Maybe you're trying to warm up milk. You want to have milk tea. I don't know why I'm on tea today. Maybe I have tea. Right? If you're trying to heat up something else, right, there's a difference with the amount of energy required. So there's 3 things there I've mentioned. mass, how much stuff you want to heat, the change in temperature, to what degree do you want to heat it to, and what the substance is. What is it are you actually trying to heat? Those three things will determine how much energy is required. Now the third one, the substance, we call this specific heat capacity. Every substance has a different specific heat capacity. Heat capacity means how much energy can be transferred to 1 kilogram of the substance to change it by 1 degree Celsius. And specific because this is a characteristic physical property, meaning it'll depend on what the substance is. Every substance has a different specific heat capacity. So you could actually use that to identify the substance. Right? Water, for example, it's a common one, has a specific heat capacity of 4,180 joules per kilogram degrees Celsius. So yeah, those are the units. So what do those units mean again? It takes 4,180 joules to heat up 1 kilogram of water by 1 degree Celsius. That's a lot of energy. Water needs a lot of energy to heat up by 1 degree. I mean, take a look at, say, metal like copper. Copper is only 380. You only need 380 joules to heat a kilogram of copper by 1 degree, whereas water, 4,180. This is why when something's like overheating or something, we pour water on it, because water can absorb the most energy per each change of degree. So we have a formula for this then. Q, which stands for, well, it's energy, right? Thermal energy, equals M, mass. C is the specific heat capacity. And delta T, your change in temperature. Now delta T, it doesn't really matter if you use Celsius or Kelvin, because 1 degree Celsius is equivalent to 1 Kelvin. Well, I should say the change in 1 degree Celsius is equivalent to 1 Kelvin. So what do I mean by that? Well, we all know that minus 273 degrees Celsius is 0 Kelvin. If you go up by 1 degree Celsius to minus 272, you're at exactly 1 Kelvin. So your change in temperature, if you're looking at Celsius, was either 1 degree Celsius or 1 Kelvin. The magnitude is still the same. So because we're always talking about a change, it does not matter if you used Celsius or Kelvins. Now, since I've never really introduced Kelvin scale in physics, that's something you'll do more in chemistry, we'll just use Celsius. Okay. Next thing I want to mention before we go off and do some example problems is the principle of heat exchange. The principle of heat exchange is just a fancy way of saying what we already know, conservation of energy. So let's say you have this much cold water, this much hot water, and you put them together. Well, the hot water is going to get a little colder, and the cold water is going to get a little hotter, and they're going to create a mixture. But the important thing is, the amount of energy must still be conserved. You cannot end up with more or less energy in the mixture than you had before you mixed it. So what this principle of heat exchange actually says is, well, if the cold water is going to get hotter, right, let's call that Q. I'll call it Q1. This is the amount of energy the cold water gains. Now the hot water is going to get colder, so let's call this Q2. That's going to be the amount of energy the hot water loses. If we take the amount of energy the cold water gains and add it to the amount of energy the hot water loses, it must equal 0 because energy must be conserved. Okay, now having said all of this, there is a lot of misconceptions people have with heat. So for example, I don't have anything metal, but let's say I had something metal. Oh, I think I do have something metal. Okay, let's say I have something metal. and I had paper towel. And if I were to ask everyone, if you were to touch it, which one feels hotter? Let's say you're sitting on a park bench on a nice warm day. Now the park bench is composed of wood and metal. Now you'd probably say the wood feels fairly cool, but if you touch the metal, it's like really hot. But what if I were to tell you that the temperature of the wood is the exact same as the temperature of the metal? What would you say? So the metal is a better conductor. The wood's a better insulator. So when you touch the metal, the heat's able to transfer faster to your hand. I can give you another example. Let's say it's a really hot day and you turn on the fan. How does that feel cold? I mean, you turn on the fan and it shoots the air at you that's in the room. It's not an air conditioner. It doesn't cool down the air. It shoots hot air at you. How does shooting hot air at you on a hot day make you feel cold? It's a little tricky because this is a little bit of a biology question as well. So you have, here's my arm, and I have a thin layer of heat being preserved above my arm. It's how we try and store heat. And if high moving wind passes over it, it removes that thin layer of heat. And therefore, I feel cooler. All right, so going over some examples. Our first example says we have an empty copper pot sitting on a burner. The pot has a mass of 1.2 kilograms and is at a temperature of 130 degrees. If the pot cools to a room temperature of 21 degrees, how much thermal energy does it release to the surroundings? So we're going to use our equation, Q equals mc delta T, to figure out how much thermal energy has been lost. So M is the mass of the pot, so 1.2 kilograms. C is the specific heat capacity, and it says it's a copper pot. So let's go back and check that. If we look at our chart here, it says the specific heat capacity for copper is 380. All right, so let's go back and we'll use 380. Joules per kilogram degrees Celsius. And then the change in temperature. So change is always final minus initial. So our final temperature is the room temperature it cools to, 21 degrees Celsius. And our initial temperature was 130 degrees. Now, notice how the units are working. So here we have kilograms. And kilograms is going to cancel here. Here we have degrees Celsius. And they will cancel here. And so we are going to be left with joules. So the units do work for us. And if we plug this into our calculator, we would get minus, using correct significant digits, 5 times 10 to the 4 joules. So where's the minus coming from? The minus represents that heat has been lost, right? Not gained. The system has lost that amount of energy, which makes sense because our pot has gone from a temperature of 130 and cooled to a temperature of 21 degrees. Now question 2 says we have a 60 kilogram sample. Let's make sure we change our units there. So we're going to make it 0.06 kilograms. Okay. 0.06 kilograms because we want everything in SI units. Of metal is heated to 100 degrees before placing it in 200 milliliters of water with an initial temperature of 10 degrees. So what are we actually doing here? Here we have water at 10 degrees. And we're going to take a piece of metal at 100 degrees and we are going to add it into the water. So this is similar to this picture over here. And if we were in school, this is actually a lab we would do. But this is called a calorimeter. And we are going to do a simulation of this lab in a couple days. Calorimeter is good at measuring energy exchange. And so if we heat up a metal, and it's easy to do. You put it in water, you heat the water to boiling. And if the water is boiling, eventually they reach some sort of thermal equilibrium. You know the metal's at 100 degrees. You take the metal and you put it in the cold water. Okay? And then you try to sort of remove the surrounding environments to try and make sure as little amount of heat is lost to the surrounding environment, because if heat is lost to the surrounding environment, that ruins the information that you're trying to collect. What you want to collect is the change in temperature of the water. So what's going to happen is, over time, the metal is going to lose energy and the water is going to gain energy until they reach some thermal equilibrium, at which point the water and metal will be at the same temperature. Now this question says what we're going to do is, once they reach a final temperature of 15.6 degrees, identify the metal. So remember, specific heat capacity is a characteristic physical property, meaning we can use it to identify what that metal is. Alright, so let's figure out the math then. How are we going to do this? So we need to solve for the specific heat capacity of the metal. Now what we know is the principle of heat exchange, which means the amount of heat that the metal loses plus the amount of heat that the water gains must be equal to 0. Just conservation of energy. So if we write this out, each equation, this is M for the metal times C for the metal times the change in temperature for the metal. Must be equal M for the water. Oh, not equal to. Oh, well, you can bring this to the other side of the equation and make it negative. So negative M for the water times C for the water times the change in temperature for the water. Now what we're trying to solve for is C for the metal, because we want to identify it. So we're going to divide both sides by its mass and its temperature. Then we've isolated it. And we're going to substitute everything we know. So let's do that. So C for the metal is going to be minus the mass of water. Oh, it doesn't tell us the mass of water. It tells us the volume of water. So you're going to have to remember grade 9, grade 9 science, where density equals mass over volume. Now they tell us volume, and we know the density of water is 1 kilogram per liter. It's a really easy density to remember. 1. Right, so rearranging, mass equals density times volume. And since density is 1 kilogram per liter, and our volume is 200 milliliters, or 0.2 liters, that means our mass is 0.2 kilograms. Alright, so we can substitute that in, 0.2 kilograms. C for water, if you remember, you can see the chart. It's 4,180, right? Specific heat capacity of water. Joules per kilogram degrees Celsius. Times the temperature change of the water. Always final minus initial. So its final temperature is 15.6 degrees. Subtract its initial temperature, which was 10 degrees. And then we need to divide that by these two terms here, because we divide both sides to isolate for C. So the mass of the metal, which we found out to be 0.06 kilograms, times by its temperature change. So again, final minus initial. The final is the same because they reach equilibrium, 15.6. But its initial was at 100 degrees. Now, if we put all of that into our calculator and do it properly, that's a lot of numbers there, okay, we will get 924 joules per kilogram degrees Celsius. So if we go back to our chart here, and we look at about 920, there it is, 9.2 times 10 to the 2, aluminum. So that means we've identified this metal to be aluminum. So our last question says the specific heat capacity of ethylene glycol is 2,200 joules per kilogram degrees Celsius. See, still not even close to water. Determine the final temperature when 1.73 kilograms of ethylene glycol at 25.4 degrees is mixed with 2.47 kilograms of the same substance at 89.2 degrees. So what we're doing is similar to this picture over here. So we have a certain amount of ethylene glycol at one temperature, and we're going to mix it with the same substance at another temperature, and we want to know the final temperature of that mixture. So that's what we need to figure out. That's what this problem is asking us. So how we're going to do that is, again, since we're mixing something, energy must be conserved. So principle of heat exchange, Q1, or the energy that one gains plus the energy that one loses, must balance. So this is, I'll write M1, so our first ethylene glycol, C1 delta T1 plus the mass of the second one. Now I could label this as C2, but I'm just going to write C1 because it's the exact same substance. They're both ethylene glycol. If you're mixing one substance with a different substance, then you would have to properly say that's C2 because they're not the same. But their masses are different and the change in their temperatures are different. But in this question, since C1 is the same and we know it's not 0, we can divide every term by C1 and just get rid of it. So we're left with M1 times delta T1. And what I'm going to do, since I can't solve for delta T1, I don't know what delta T1 is, I don't know what delta T2 is, I'm going to expand it. And I've always said it's always final minus initial. So the final temperature of our first substance minus the initial temperature plus M2, and delta T2 I will expand again, final minus initial must be equal to 0. Now the final temperatures of both substances will be the same because they reach thermal equilibrium. The initial temperatures won't. So I'm going to call this T1 for our first substance and this one, or sorry, Ti for our second substance. Just so I know that they're different. Right? You can always throw in whatever subscripts you want. There's no rule for what subscripts you use. Just to make sure you're telling yourself and you remind yourself these are different values. But the TF is the same, and that's what I'm trying to solve for. So right now I have to try and solve for TF. So I'm going to expand each and just distribute the masses into those brackets, like so. So this will give me M1 TF minus M1 T initial 1 plus M2 TF minus M2 T initial 2, which equals 0. And since I'm solving for, I'm using so many colors, since I'm solving for TF, what I'll do is I'll take those two terms and factor out a TF. So TF multiplied by M1 plus M2. Add the other terms, this one and this one. I know those values, so I can bring them both to the other side of the equation, and they'll become positive. So we have M1 Ti1 plus M2 Ti2. And now I just divide both sides by this bracket, and I can get TF equal to, so M1, okay, so that's, is it 1.73 kilograms? And it doesn't really matter which one you label to be 1, which one you label to be 2, as long as you're consistent throughout the problem. Times the initial velocity, which is, sorry, not velocity, the initial temperature, 25.4 degrees Celsius, plus the mass of our second mixture, which is 2.47 kilograms, times its initial temperature, which is 89.2 degrees, And then we're going to divide by this bracket, which is the sum of their masses, which would be 1.73 kilograms plus 2.47 kilograms. And again, lots to plug in our calculator, but we will get 62.9 degrees Celsius. And this makes sense, right? The ethylene glycol that started off at 82 cooled to 62. 89 to 62. And the other one that started at 25 heated to 62. So it's a temperature in between the two. If you were to get a temperature greater or less than both of them, energy is not conserved, you know you did something wrong. So it's a good way to check your answer.